Hello everyone, my name is Do, and this presentation is about our work, maximizing the correlation, extending Grothendieck's inequality to large domains. This is a joint work with Roy Schwartz, and we are from the Computer Science Department in the Technion. Okay, so let's start. This work is about a problem of correlation clustering. And in the model of correlation clustering, we're basically given a graph, an undirected graph, where the edges are labeled by plus or a minus sign. Plus sign indicates that the two nodes are similar, and the minus sign indicates that the nodes are not similar. So the goal is to find a clustering of the graph, which is basically the partition of the nodes in the graph, that agrees the most with the labels of the edges. For example, a plus edge should be inside a cluster, and a minus edge should go across clusters. Okay, let's see an example. Here we have a graph. Some of the edges are labeled with a plus edge, a plus sign. Some of the edges are labeled with a minus sign. And we also have some weights on the edges. Throughout the talk, I may not always talk about the weights, but it's there. So, okay, so we want to find the clustering of this graph. So let's see, for example, this clustering. Here we have 4 clusters. We can see that some of the plus edges are within the cluster, some of the minus edges are within the clusters too, and so on. It is important to notice that a perfect clustering does not always exist. For example, we can have this triangle, this plus plus minus triangle, and no matter how you try to cluster the graph, you will always disagree with one of the edges. So we cannot always cluster the graph in a way that agrees with all the edges. Okay. So how exactly do we measure how good the clustering is? So the first thing we can do is to count the agreements. What are the agreements? The agreements are the edges that are classified correctly. For example, a plus edge that resides within a cluster, and a minus edge that go across clusters. Here we have all the agreements in bold, and all the rest of the edge are not agreements. So the rest of the edge are called the disagreements. The disagreements are the edges that are classified incorrectly. And here we have the, for example, the plus edge that go across clusters and the minus edges that are inside clusters. So these are the disagreements. So now we have the agreements and we have the disagreements, and we can define the objectives. So what are the objectives? The first objective that we can talk about is called max agree. And in this objective, we want to maximize the number of agreements. We want to find a clustering that maximizes the number of agreements. Another objective is called mean disagree, and we want to find a clustering that minimizes the number of disagreements. So these two objectives are similar, but they are quite different in the hardness of the problem. And in the third objective, so the third objective is called MaxCorr, and we want to maximize the correlation. What is the correlation? The correlation is the difference between the number of agreements and the number of different disagreements. So you take all the agreements in the clustering, all the sum of the weights of the agreements, and you subtract the sum of the weights of the disagreements, and this is what you get. This is a correlation. So we want to find a clustering that maximizes this value, the correlation. Okay. So let's talk a little bit about the motivation for this problem or this model. So much work was done on correlation clustering. There were many approximation algorithms for these objectives on various types of graphs, such as general graphs, complete graphs, bipartite graphs, hypergraphs, so on. It also has some practical application like image segmentation, crossing link detection, clustering gene expression patterns, and so on. And it also covers some classic graph problems like mean ST cut, multi-way cut, multi-cut. You can define some other variants of correlation clustering, and it will capture some other graph problems. For example, if you take max agree, or you want to maximize the agreement, and you limit the number of clusters in the output to be at most 2, then this problem will capture the max cut problem. Okay, so in our work, we studied the problem of MaxCorr. Remember, this is the third objective. And we studied on bipartite graphs. We also extend this problem to MaxCorr, and this problem is where the number of clusters in the output is limited to be at most k, where k is some constant. We present approximation algorithms for these problems, and we also show the relation between these problems and the Grothendieck's inequality. We'll get to that later, if you're not familiar with this inequality. Okay. So what happened in the previous works? So Charika and Wirth studied the problem of maximizing a quadratic form. In this problem, we are given a matrix, an n by n dimensional matrix, and we want to find a vector x, an n-dimensional vector over 1 and plus, minus or plus 1, that maximizes the form x transpose bx. And what Charika and Wirth showed that there is an approximation algorithm with a guarantee of omega of 1 over log n for this problem. And then they showed a very elegant reduction from MaxCorr to the maximization of a quadratic form. So what they did is you can take the graph with the signed and weighted edges, and you define the following metrics. You set Bij to be equal Wij if there is a plus edge that connects between I and j. And if there is a minus edge, you put the minus of the weight in the entry of the matrix. Okay, and if there isn't if there's no edge, you just put 0. Okay, so what is the reduction? You build this matrix, and then you solve this program. You have to find you solve this quadratic maximization form. You find this vector x. And then you define this clustering, C1 and C2, to be the clustering that's induced by the solution. So you have a vector x with some 1s and minus 1s. So you take all the nodes that get 1 in one cluster and all the minus 1s in the other cluster. And this is the clustering. So, and in the next stage, you return the best of this solution and the old singleton solution. The old singleton solution is the clustering that every node is in a different cluster. Okay. So what they showed is that if you do this reduction and you have an alpha approximation for the problem of maximization of a quadratic form, then this will result in an alpha over 2 plus alpha approximation for the MaxCorr problem on general graphs. So in total, you get an approximation of 1 over log n, omega of 1 over log n, for MaxCorr on general graphs. Okay, this is what Charika and Wirth did. So we want to go from maximizing of quadratic form and general graphs to bipartite forms and bipartite graphs. So we define the following problem. It's called a maximization of a bipartite quadratic form. We denote it by max biquad. So in this problem, you are given a matrix A. It is an n by m dimensional matrix, And you have to find two vectors, x and y. X is an n-dimensional vector over plus or minus 1, and y is an m-dimensional vector over plus or minus 1. And you want these vectors to maximize the form x transpose a y. So it's very similar to the previous problem. And you can see, or maybe you can stop for a minute and see that this problem of maximizing a bipartite quadratic form is actually equivalent to the problem of MaxCorr on bipartite graph. This is where you're given a bipartite graph, and you want to find a clustering that maximizes the correlation, but this clustering is limited to at most 2 clusters. Okay. So how do we solve this problem? How do we solve this max biquad problem? You usually do it by rounding the natural semi-definite program. What is the natural semi-definite program? Instead of plus or minus 1 signs, you have unit vectors. And instead of maximizing this form, x transpose ay, you want to maximize a form that instead of xi times yj, you have the inner product between the vector xi and the vector yj. So this relates directly to Grothendieck's inequality. This is exactly, in fact, Grothendieck's inequality, but it's almost inequality. And what it says, the Grothendieck inequality, it says that there is a universal constant, kg, such that for every matrix A, the following inequality holds. So on the right side, what do we have on the right side? We have this value. We want to find the vectors x and y that maximize this form. This is the bipartite quadratic form. This is exactly what we had in the previous slide. And on the left side, what we have is the semi-definite program for the max biquad problem. So we have this n plus m unit vectors, and we want to maximize this form. And what Grothendieck's inequality say is that the left-hand side of this equation or inequality is not much larger than this side. Obviously, the left side is bigger than the maximization of a bipartite quadratic form, but it's not much larger, and it's only larger by a constant. Okay, so if you want to know what is the value of this constant, we actually don't know its value. We only know its first 2 digits, and we can bound its value. So Kervin showed that this constant is at most 1.782, and his result is actually algorithmic, and it shows that you can in fact take this set of unit vectors and round them to have an integral solution from the right side, and you will not lose too much. So basically, a polynomial time approximation algorithm. And we also know that this constant is at least some factor like 1.76. Okay, so let's try to use this approach for the problem of MaxCorr on a bipartite graph. So we have Kervin's algorithm for maximizing a bipartite quadratic form that achieves a 0.5611 approximation. And if you use it and the Charikov width reduction, this will yield a 0.219 approximation for MaxCorr on a bipartite graph. So it's a nice approximation, but we can do better than this. So it is important to note that there is a small barrier here because the Grothendieck constant is bounded by 1.769. So if you want to use this approach and round the semi-definite program to solve the max biquad problem and then use the reduction, you cannot hope for a better approximation then this number, 0.2296, this is after you plug the bound of 1.769. So you can't hope for a better approximation than this one. In addition, the algorithm may output a large number of clusters. Remember that we choose between the clustering of the maximization of the bipartite product form and the clustering of the whole singleton clustering. So it may output a large number of clusters. And if we want to solve the MaxCorr problem, where the number of clusters in the output is limited to be at most k, we cannot use this algorithm. So what do? We depart from this approach and we try something a little bit different. Okay. So before I show you what we did, I will talk about the results. So the first result is that there is a polynomial time 0.254 approximation algorithm for MaxCorr on bipartite graphs. So this improves the 219 approximation, and it also goes beyond the 2296 barrier of this approach. Okay, and the second result, or basically an extension of the first result, is approximation for MaxCorr. And we can see in the table that for k equals 2, we have the same guarantee as in Grothendieck's algorithm. And as k goes bigger, the approximation factor decreases. Okay. And for arbitrarily large k, we reach the approximation factor of theorem 1. And also, these results are a natural extension of Grothendieck's inequality to large domains. What does it mean exactly, large domains? If you go back to this inequality, here you can see that, for example, the vector x and y are over a plus or minus 1. You can think of it like x and y can have a larger values. Not only plus or minus 1, you can have different values. Okay, techniques. The first thing that we do is we suggest a natural SDP relaxation for MaxCorr problem. And then we show how to round the solution for this problem and obtain a clustering. So how do we do it? We extend Grothendieck's method to allow more than 2 clusters in the output. And then we show how we can adapt this relaxation in this algorithm for the problem of MaxCorr, when you want only most k clusters in the output. So here is the SDP relaxation for MaxCorr. And you can say that we have a vector for every node in the graph. And what we want is that every vector will be a unit vector. And the inner product between every 2 vectors will be non-negative. And basically, what this means that all the vectors lie in the same orthant or hyperoctant. Okay, so let's take, for example, a clustering. And we can assign for every cluster and for every node in the cluster, we can assign this a different unit vector, a standard unit vector. You can see that if 2 nodes are in the same cluster, then the vectors will be the same vector, and the inner product between these vectors will be 1. And if 2 nodes are in different clusters, then they will be assigned 2 different standard unit vectors, and the inner product will be 0. So if you look at the objective here, you can see, for example, for this for a plus edge, that if 2 nodes are in the same clustering, then this will be 1, and will donate the edge of the weight. And if they are in different clustering, this will be -1, and we will pay the edge of the weights. So this is exactly the either the agreement or the disagreement. Okay, so this is the relaxation for the problem. And let's see the algorithm. So what happens in the algorithm? First, we are given a graph. We have a bipartite graph. where some of the edges are labeled by a plus sign, and the rest of the edges are labeled by a minus sign. So the first thing that we do is we solve the SDP relaxation. And what is the result? The result is a fractional solution. We have a set of vectors, y1 to yn. And you can see here in this drawing that these vectors are all unit vectors in a high-dimensional vector space. And here you can see the three-dimensional sphere, but imagine it is a high-dimensional hypersphere. Okay. So in the next stage of the algorithm, what we do, and this is the most important part of the algorithm, is that we transform the vectors. You can see that they shifted a little bit, and we have a new set of vectors, and the new set is also a set of unit vectors, and this transformation is actually based on the bipartite structure of the graph. This is the only part in the algorithm that we are using the fact that the graph is bipartite. If you look at the relaxation, the SDP relaxation, there's no sign for the structure of the graph. It's perfectly good for general graphs. I don't know how to round this relaxation for a general graph, but it's also good for general graphs. Okay, so here in the third stage, what we did is we transformed the vector. They shifted a little bit, and this will help us to achieve a good approximation factor. Okay, so what happened in the next stage? We want to somehow cluster the nodes in the graph. We want to cluster these vectors. So how do we do it? We draw a random unit vector, and it will split the hypersphere. It's a hyperplane that goes through the origin. It will split this hypersphere into two pieces. And you can see all the green vectors that are above the hyperplane. These are, in fact, one piece. And all the red vectors, this is another piece of the hypersphere. And now we have two clusters, right? So we can stop here, but this will not be a very good approximation algorithm. So what do? We want to cluster it again. So how do we do it? We randomly choose one of the clusters. We randomly choose one of the pieces of the hypersphere, and we draw another hyperplane, and it splits it again. So here in this example, we randomly chose this the upper part, and we split it with another hyperplane. So the result is three pieces. We have three pieces of the hypersphere. You can see the green vectors and the blue vectors are in two different sides of the blue hyperplane. Okay, and this will be the result of the algorithm. The result is the clustering that is induced by these three pieces of the hypersphere. Okay, so you can see in the analysis of the algorithm that this algorithm, with the right choice of the transformation, achieves the 0.254 approximation for the MaxCorr on bipartite graph. All the analysis of the algorithm is discussed in our paper. Okay, and in addition, you can take this SDP relaxation, and you can take this algorithm and extend it to the MaxCorr problem with some not too big modifications. In addition, I did not discuss it, but you can show that these two problems are in fact some extensions of Grothendieck's inequality. Okay. So thank you.